League of Legends features a multitude of stunning visual effects. In this video I will demonstrate how to recreate Lux's light binding effect in Unity with the VFX Graph and Shader Graph. To achieve this effect we will need a ring model, an ornamental texture and a ray texture to link the rings together. I created both of these textures in Procreate. The ray texture is basically just a transparent one drawn in white brush strokes. An ornament texture can easily be created in Illustrator. Alternatively, there are also royalty-free ornament textures available on the asset stores. Let's begin by creating the ring model in Blender. Create a circle with 64 vertices. Fill this circle with a single face and proceed to inset the face to form a ring shape. To ensure it looks like a ring model, delete the inner face. Let's create a material so we can edit and verify our UVs. For the base color, select the ornament texture you previously designed. When you preview the material, you may notice that the ornament texture isn't visible yet. This is due to incorrect UV mapping. Open another side window and open the UV editor. Be sure to select the synchronization button so that any selections you make in the UV editor are also reflected in the scene view. Select all faces in the scene view. Press U and select Unwrap. Press U again and reset the UV. This is a bit too much, so we should divide the faces. Then let's scale the UV on the x-axis and use a scale of 0.125. We use this specific value because we want the texture to repeat 4 times across 32 faces in total. When you have done everything correctly, you should see the ornament texture on the model. Save the Blender model and rename it. Also make sure to apply all the transforms of the model. Finally, export the model as an FBX to the Unity project. Awesome! Back in Unity I created a URP project, but this should work also with the HDRP version. Now, in order to create the visual effect of a glowing ring, we need a shader. Create a new shader using the Shader Graph. Use the URP lit shader graph for this. As the ring features a dissolution effect and we also need it for the rays, let's create a shared shader graph for the dissolution calculation. Create a subgraph for this. You should now have a lit URP shader graph for the ring and a subgraph for the dissolution. Open both of them. In order to preview our shader, we change the preview mesh to our ring model. Change the surface type to be transparent, enable alpha clipping and disable any shadow related features. Also, don't forget to enable VFX support. For the alpha clipping, set it to 0. Let's start by creating a variable for the texture. Choose texture 2D and call it main text. This will be our ornament texture. Also create a color variable and a float for the dissolution. We want to control the dissolution later on in the VFX graph. Drop the dissolution variable and main text variable into the graph. Connect the texture with a simple texture node. Don't forget to apply our ornament texture as a default for the main text, else the preview will not work. Okay, cool. Let's colorize the texture a bit and use an add node where we add the color to the texture color. As my ornament main texture color is black, this will work fine. If yours is white, you will need to use a multiply node instead. For the color, choose the color you like and apply HDR and increase the intensity a bit to make it glow. Finally, connect the color to the base color output and the emission output on the fragment node. Now, when we have done that, let's take a look at the dissolution effect itself. Drop the dissolution graph into the existing graph and switch to the dissolution graph so we can edit them. For the graph, add the dissolution as a float input parameter. The dissolution works by applying a noise to the existing alpha of our ornament texture. For a dissolution value of 0.5, it will apply 50% of the noise as an additional alpha value. Connect the dissolution to a remap node and change the remap values to be between 1 and 5. Then connect this to a multiply node and create a noise node. Change the noise scale to 50. Finally, connect the multiply node to a 1- node. This will essentially reverse the dissolution value. So a 1 means 100% dissolution and 0 means 0 dissolution. Clamp the final results between 0 and 1. Save the asset and go back to our cage ring shader. Connect the dissolution to our new dissolution graph parameter and connect the whole graph with a multiply node. We will essentially multiply any existing alpha value that is on the ornament texture with the alpha values coming from the noise pattern. Also, I forgot to change the final output of the dissolution graph to be a float instead of a vector. We are nearly done with the ring shader itself. Just plug the final alpha into the alpha channel, save the asset, and you should be able to preview the new shader. For a small test, create a new material by right-clicking on the shader graph itself and apply the material to the ring model. As you can see, the alpha and glow should be working correctly. The dissolution can be tested by changing the dissolution on the material itself. Okay, cool, you don't need the material anymore, so this can be safely deleted again. Now we get to the fun part by creating our VFX graph. For this, you will need the VFX graph installed. The graph will create the ring model 2 times and apply the dissolution shader over a lifetime of around 5 seconds. Create a new visual effect graph and open it. It will show a default particle system, which we will change a bit. The system itself should be renamed to Ring. Remove the existing spawn node and instead create a single burst spawn by pressing the spacebar. Change the count to be 2, so 2 rings are created. For the initialize node, remove all the existing nodes so we can start fresh. Add a set position node and set lifetime node. For these nodes, we will create new parameters. Create one float parameter for the lifetime with a default value of 5 seconds and connect it to the set lifetime. In order to change the height for each of the rings, we need the spawn index, so we can multiply its spawn index with a custom height. Create a height parameter in order to achieve that. Also set a default value of, for example, 1.5. Also, the first ring should also have a height which is not 0, so we can clearly see the ring and it doesn't interfere with the ground. To achieve that, we need a clamp node and clamp the height to be a minimum of 0.15 for the first ring. The final position should be plugged into the Y position. As the rings slowly rotate, we can also add an add angle node to the update particle system. For this, again, create a parameter and set a default value of maybe 0.1. Again, we set the parameter to the Y node, so it will rotate around its local Y axis. As we use a mesh for the particles, we don't need the existing output particle. Instead, create an output particle URP lit mesh. Drop the ring shader graph into the new output particle and also add the texture to it. Don't forget to change the mesh to use the new ring model. Awesome! When you save the VFX graph and drag it into a scene, you should see 2 rings now. These rings should be very small as we forgot to set the size. You can set the size of 1 on the output particle node. Okay, now the only thing left for the ring is the dissolution effect itself. To control the dissolution, we need to control the time. Let's divide the total time by the current lifetime. The result will be a percentage of the time that has passed. As we want to show the rings for at least 50% of its lifetime, we need to map the dissolution effect to the first 25% and the last 25% of its lifetime. The threshold parameter we now create represents the percentage of when the dissolution started and when it ended. In order to map the current lifetime percentage to either a dissolution effect or none, we need to essentially do a big if statement. For this, we create a visual effect operator, as it's highly likely that we need this calculation in other visual effects. Let's call it remap operator and open the graph. Here's a pseudocode function of how remapping will work. We will create the exact same function like you see in the code in the graph. If the incoming value is less than the threshold, we will decrease the dissolution over time. Then, until the threshold is met again, the dissolution will be 0. When the dissolution starts again, it will increase to 100% again. Let's remove every existing functionality from the operator, remove one of the outputs. Rename the input parameter to be value and set a default of 0.5. Create another input value for the threshold. Rename the output parameter to something like remap value, for example. Let's rebuild the functionality like I showed you before. Connect the value to a compare node and change it to less or equal. Connect also the threshold. Then create a branch node which is exactly behaving like an if statement. If the condition is true, we will return the division value between them. If the condition is false, we will do another comparison for the last threshold, therefore we check if the value is higher than 75%. Create another branch node to check the condition. For the false value, return a 1. If the condition is true, we are in the last 25% of the lifetime and need to increase the dissolution again. Finally, connect the result to the remap value output. Save the asset and let's connect the remap operator correctly. Essentially, we only need to connect the remap value to the dissolution value of our ring shader. We overlooked the 1- part of the calculation, which disrupts the formula. To fix this, simply insert a 1- node to the result and it should work correctly. The effect appears during the first 25% of its lifetime and disappears during the last 25%. Now, let's layer on some additional effects. The cage ability also includes ascending bubbles. Create a new system and let's add a constant spawn rate of 25 particles per second. We initialize the particles on the ring by adding a set position circle node. The circle will have an incorrect rotation, so let's rotate it to match the rotation of our rings. Let's also decrease the radius a bit, else the bubbles would appear on the edges instead of inside of the ring. Set a random lifetime between 1 and 2 seconds for the bubbles and also a random angle. Finally, we scale them randomly so some of them appear bigger and some are small but look like a spark. The update system is very simple for this one, consisting only of a gravity node that steadily increments the Y position. Okay, let's render the particle with a default output particle quad. Set the same color like the output particle mesh and create a multiply size over life node. The curve should increase the size up to 1 and then decrease it, like a typical bell curve. Great, now we should also have some bubbles. We can improve them later on. Let's finally also create some rays. Create a new spawn system. At a constant spawn rate and also a single burst spawn, so some rays appear directly when the cage is created. For the initialized particle, we will basically copy the set position and circle node from the bubbles, as the rays should also appear inside the rings. Let's increase the position Y value a bit so the rays are positioned in the middle of the cage. Then, set a random scale. We use 1.7 for the x-axis so they match the height of the cage, and a value of 0.01 and 0.15 in the y-axis to make some of them bigger and some of them smaller. Also set a size of 1, as the default size of 0.1 is a bit too small for this. The lifetime can also be random, but I opted for a fixed lifetime of 2 in this case. For the angle, We should rotate the rays by 90 degrees so the rays look upward. Okay, nice. Now we only need to render the rays. Let's use an output particle quad. Like always, we copy the color again. As an improvement, you should also create a parameter for this color so you can create more variations later on. Create a multiply alpha over live node so the rays appear and disappear smoothly. As you could imagine, we need a shader for the rays itself. As the shader doesn't work correctly with the set alpha over live node, we also need to input the alpha value of the particle to the shader. Create a new shader graph. For this, it will be enough to create a simple unlit shader. As you can see, I forgot to import the ray texture, so I've done that. Again, like the last time, enable VFX Graph support in the shader itself. We want to move the rays upwards over the lifetime so it looks like the cage rings are connected to each other. For this, we need to create a time node. Create a speed variable of type vector2 and set a default value of -0.5 on the x-axis. The speed in combination with the time will scroll the texture across the sprite and give the illusion of movement. Multiply the time with the speed. Add the UVs to this result. To make use of the UVs, we will need a texture variable once again. We will sample the texture using the adjusted UVs. Now let's create an alpha parameter for the alpha over time node from the VFX graph to smoothly generate the rays. Furthermore, we have the option to multiply the texture's colors with a custom color of our own. By setting the default texture to the ray and using a default HDR color, we should be able to preview our scrolling texture seamlessly. Let's connect the colorized result to the base color input and the corresponding alpha result to the alpha value. And let's not forget also to support the dissolution effect like with the other shader. For this we just need our dissolution graph again and a dissolution input variable, and it should work out of the box. Great! Now back to our VFX graph, we can finally use our newly created shader. We just need to drop the shader graph into the quad and connect the alpha accordingly. Also connect the dissolution to the shader. The rays don't appear to work correctly. As you can see, the particles are created as we can see their shadows. The first issue is our texture. We forgot to connect the ray texture to the shader. The second issue is happening due to the rays not being sprites but rather normal quads. In the ray shader, change the material to be an unlit sprite instead. Now the rays are working correctly. The VFX is done, but we can add small improvements. Let's disable the generation of new particles when the lifetime is over. This is achieved through a comparison between the lifetime and the current total time. The resulting boolean can be used as an activation or deactivation switch for all the particle systems. Simply connect it to the particle system and the particles will cease to generate once the total time surpasses the effect lifetime. Awesome! Finally, I enhanced the color intensity slightly to give it a brighter appearance. I hope you enjoyed this video. If you want to see more particle effects like this, please like and subscribe, and see you next time.